async await pattern. The idea behind async await is to let the programmer write code that looks like normal synchronous code, but is turned into asynchronous code by the compiler. It works based on two keywords, async and await. The async keyword can be used in a function signature to turn a synchronous function into an asynchronous function that returns a future. The above is roughly translated by the compiler to this. This keyword alone wouldn't be that useful. However, inside async functions, the await keyword can be used to retrieve the asynchronous value of a future. So this await is like a yield. Let's just take a quick peek in the playground here. Yeah, this isn't really reading a file. This is just creating a file, or creating a string rather, that is a future, just to try it out. Oh, that's the same one. Okay. This must be the wrong link then. The wrong link to the gist. Okay. This function is a direct translation of the example function that used combinator functions from above. Using the await operator, we can retrieve the value of a future without needing any closures or either types. As a result, we can write our code like we write normal synchronous code, with the difference is that this is still asynchronous code. State machine transformation. What the compiler does behind the scenes is to transform the body of the async function into a state machine, with each await call representing a different state. For the above example function, the compiler creates a state machine with the following 4 states. So we have a start state, awaiting on foo.text, so this line, right? Waiting on bar.text, and then the end state. Each state represents a different pause point of the function. The start and end states represent the function at the beginning and end of its execution. The waiting on foo state represents the function is currently waiting for the first async read file result. Similarly, the waiting on bar state represents the pause point when the function is waiting on the second async read file result. The state machine implements the future trait by making each poll call a possible state transition. Okay, so we sit waiting on foo. Is it ready? If no, then we keep staying in this loop. If it is ready, then we go to the next state. And we loop here until bar is ready, and then we exit. What's this? The diagram uses arrows to represent state switches and diamond shapes to represent alternative ways. For example, if the foo text file is not ready, the path marked with no is taken, and the waiting on foo text state is reached. Otherwise, yes path is taken. The small red diamond without caption represents if content len is less than 100. Oh, okay. Yeah. Branch of the example function. Right, so we can skip over it. Right, we don't need to call this function. I got it. We see that the first poll call starts the function and lets it run until it reaches a future that is not ready yet. If all futures on the path are ready, the function can run till the end state where it returns the result wrapped in a poll ready. Otherwise, the state machine enters a waiting state and returns poll pending. On the next poll call, the state machine then starts from the last waiting state and retries the last operation. Okay. Saving state. In order to be able to continue from the last waiting state, the state machine must keep track of the current state internally. In addition, it must save all the variables that it needs to continue execution on the next poll call. This is where the compiler can really shine. Since it knows which variables are used when, it can automatically generate structs with exactly the variables that are needed. As an example, the compiler generates structs like the following for the above example function. Compiler generated state structs. So it created a start state, awaiting on foo. I'm sure it's not named this, right? It named some bizarre internal name. Minlen is the variable it needs to capture. And footext future is this thing. And then waiting on bar, then it needs to capture the content of the previous file. Okay. In the start and waiting on a foo.txt states, the min_len parameter needs to be stored because it's required for the comparison with content.len later. The waiting on foo state additionally stores a foo_text future, which represents the future returned by the async read file call. This future needs to be polled again when the state machine continues, so it needs to be saved. The waiting on bar state contains the content variable because it's needed for the string concatenation after bar.text is ready. It also stores a bar_text future that represents the in-progress load of bar.text. The struct does not contain the min_len variable because it is no longer needed after the content_len comparison. In the end state, no variables are stored because the function did already run to completion. Keep in mind that this is only an example for the code that the compiler could generate. The struct names and field layout are an implementation detail and might be different. Right. The full state machine type. While the exact compiler-generated code is an implementation detail, it helps in understanding to imagine how the generated state machine could look for the example function. We already defined the structs representing the different states and containing the required variables. To create a state machine on top of them, we can combine them into an enum. We define a separate enum variant for each state and add the corresponding state struct to each variant as a field. To implement the state transitions, the compiler generates an implementation of the future trait based on the example function. So this is the return type, and then here's our poll function. And this is the pin thing again, which I'm sure we're going to get to very soon in the current context. Where did we use CX? I don't see it. Oh, maybe that's when we have to handle the pinning. The output type of the future is string because it's the return type of the example function. To implement the poll function, we use a match statement on the current state inside a loop. The idea is that we switch to the next state as long as possible and use an explicit return poll pending when we can't continue. For simplicity, we only show simplified code and don't handle pinning, ownership, lifetimes, etc. So this and the following code should be treated as pseudocode and not used directly. Of course, the real compiler-generated code handles everything correctly, albeit possibly in a different way. To keep the code excerpt small, we present the code for each match arm separately. Let's begin with a start state. Example state machine start, let foo text futures async read file. So this gets a future. And then we look at we set our new state variable to this, and then set self to the current state. Okay. So, to the self to the next state that we need to deal with. The state machine is the start state when it is right at the beginning of the function. In this case, we execute all the code from the body of the example function until the first await. To handle the await operation, we change the state of the self state machine to waiting on foo.text, which includes the construction of the waiting on foo_text struct. Since the match self statement is executed in a loop, the execution jumps to the waiting on foo_text arm next. So then it's checking the future to see if it's pending, and if it is, we return pending, and if it's ready, then we do the body of the next set. Okay, in this match arm, we first call the poll function of the foo_text future. If it's not ready, we exit the loop and return poll pending. Since self stays in the waiting on foo_text state, in this case, the next poll call on the state machine will enter the same match arm and retry polling foo_text future. When the foo_text future is ready, we assign the result to the content variable and continue to execute the code of the example function. If content_len is smaller than the min_len saved in the state struct, the bar text file is read asynchronously. Right, that's this line here. We again translate the await operation into a state change, this time into the waiting on bar text state. Since we're executing the match inside a loop, the execution directly jumps to the match arm from the new state afterwards, where the bar text future is polled. In case we enter the else branch, No further await operation occurs. We reach the end of the function and return content wrapped in a poll ready. We also change the current state to the end state. The code for waiting on bar text looks like this. Similar to the waiting on foo text state, we start by polling the bar text future. If it is still pending, we exit the loop and return poll pending. Otherwise, we can perform the last operation of the example function, concatenating the content variable with the result from the future. We update the state machine to the end state and then return the result wrapped in poll ready. Finally, the code for the end state looks like this. Panic. Future should not be polled again after the return poll ready. Therefore, we panic if poll is called when we are already in the end state. We now know how the compiler-generated state machine and its implementation of the future trait could look like. In practice, the compiler generates code in a different way. In case you're interested, the implementation is currently based on generators, but this is only an implementation detail. The last piece of the puzzle is the generated code for the example function itself. Remember, the function header was defined like this. Since the complete function body is now implemented by the state machine, the only thing the function needs to do is to initialize the state machine and return it. The generated code for this could look like this. Right, so we're going to start in the start state. The function no longer has an async modifier since it now explicitly returns an example state machine type which implements the future trait. As expected, the state machine is constructed in the start state and the corresponding state struct is initialized with the min-len parameter. Note that this function does not start the execution of the state machine. This is fundamental design decision of futures in Rust. They do nothing until they are polled for the first time. Okay, that's good to know. Now we're going to talk about pinning. All right, we already stumbled across pinning multiple times in this post. Now is finally the time to explore what pinning is and why it's needed. Self-referential structs. As explained above, the state machine transformation stores the local variables of each pause point in a struct. For small examples like our example function, this was straightforward and did not lead to any problems. However, things become more difficult when variables reference each other. For example, consider this function. Okay. This function creates a small array with contents of 1, 2, and 3. Oh, why can't I select that? Okay. It then creates a reference to the last array element and stores it in an element variable. Next, it asynchronously writes the number converted to a string to a foo text file. So the async write file, foo text element to string. Finally, it returns the number referenced by element. Okay. Since the function uses a single await operation, the resulting state machine has 3 states: a start, the end, and the waiting on write. The function takes no arguments, so the struct for the start state is empty. Like before, the struct for the end state is empty too because the function is finished at this point. The struct for the waiting on write state is more interesting. It contains the array and the address of the last array element. We need to store both the array and the element variables because element is required for the return value and array is referenced by element. Since element is a reference, it stores a pointer, memory address, to the referenced element. We used OX1001C as an example memory address. Here, in reality, it needs to be the address of the last element of the array field, so it depends on where the struct lives in memory. Structs with such internal pointers are called self-referential structs because they reference themselves from one of their fields. The problem with self-referential structs. The internal pointer of our self-referential struct leads to a fundamental problem, which becomes apparent when we look at its memory layout. The array field starts at address 10014, and the element field at address 10020. It points to address 1001C because the last array element lives at this address. At this point, everything is still fine. However, an issue occurs when we move the struct to a different memory address. We move the struct a bit, so it starts at address 10024 now. This could, for example, happen when we pass the struct as a function argument or assign it to a different stack variable. The problem is that the element field still points to the address 1001C, even though the last array element now lives at address 1002C. Thus, the pointer is dangling with the result that undefined behavior occurs on the next poll call. Possible solutions. There are three fundamental approaches to solve the dangling pointer problem. Update the pointer on move. The idea is to update the internal pointer whenever the struct is moved in memory so that it is still valid after the move. Unfortunately, this approach would require extensive changes to Rust that would result in potentially huge performance losses. The reason is that some kind of runtime would need to keep track of the type of all struct fields and check on every move operation whether a pointer update is required. Store an offset instead of self-references. To avoid the requirement for updating pointers, the compiler could try to store self-references as offsets from the struct's beginning instead. For example, the element field of the above waiting on write state struct could be stored in the form of an element offset field with the value 8, because the array element that the reference points to starts 8 bytes after the struct's beginning. Since the offset stays the same whenever the struct is moved, no field updates are required. The problem with this approach is that it requires a compiler to detect all self-references. This is not possible at compile time because the value of a reference might depend on user input. So we would need a runtime system again to analyze references and correctly create state structs. This would not only result in runtime costs, but also prevent certain compiler optimizations so that it would cause large performance losses again. Forbid moving a struct. As we saw above, the dangling pointer only occurs when we move the struct in memory. By completely forbidding the move operations on self-referential structs, the problem can be also avoided. The big advantage of this approach is that it can be implemented at the type system without additional runtime costs. The drawback is that it puts the burden of dealing with move operations on possibly self-referential structs on the programmer. Maybe this should be 4 to avoid the on. Okay. Because of its principle to provide zero-cost abstractions, which means that the abstractions should not impose additional runtime costs, Rust decided for the third solution. For this, the pinning API was proposed in RFC 2349. In the following, we will give a short overview of this API and explain how it works with async, await, and futures. Heap values. The first observation is that heap allocated values already have a fixed memory address most of the time. They are created using a call to allocate and then referenced by a pointer type such as box T. While moving the pointer type is possible, the heap value that the pointer points to stays at the same memory address until it is freed through a deallocate call again. Using heap allocation, we can try to create a self-referential struct. Let mute heap value box new self-referential self pointer 0 is const. 0 is const underscore. Let pointer is a reference to heap value is const self-referential. Heap value self pointer is pointer. Println heap value at this. Internal reference there. And there's struct self-referential. Let's try it on the playground. Can I run it? What will it print out? Well, I mean, it works, right? Heap value and heap value self pointer. So now this is pointing, the value on the heap is there. That's the address. And here's the address of self pointer, which points right back to itself. All right. We can get rid of that. We create a simple struct named self-referential that contains a single pointer field. First, we initialize the struct with a null pointer and then allocate it on the heap using box new. We then determine the memory address of the heap allocated struct and store it in the pointer variable. Finally, we make the struct self-referential by assigning the pointer variable to the self pointer field. Yeah. And none of this is unsafe. That's interesting. Finally, we make the struct self-referential. Okay. When we execute the code on the playground, we see that the address of the heap value and its internal pointer are equal, which means that the self pointer field is a valid self-reference. Since the heap value variable is only a pointer, moving it, for example by passing it to a function, does not change the address of the struct itself, so the self pointer stays valid even if the pointer is moved. Okay, however, there's still a way to break this example. We can move it out of a box or replace its content. The stack value is, if you call mem replace. And again, that's not unsafe. And now we say println this and println that. Okay. So we can add this to the playground, right? Yeah, so now the value is here, but the reference is still pointing to the old reference. So now it's broken. And that's not unsafe code. Right? Because we didn't have to do any unsafes. Here we use the memReplace function to replace the heap allocated value with a new struct instance. This allows us to move the original heap value to the stack, while the self pointer field of the struct is now a dangling pointer that still points to old heap address. When you try to run this example on the playground, you'll see that the printed value at and internal reference lines show indeed different pointers. So heap allocating a value is not enough to make self-references safe. The fundamental problem that allowed the above breakage is that the box T allows us to get a mut T reference to the heap allocated value. This mut reference makes it possible to use methods like memReplace or memSwap to invalidate the heap allocated value. To resolve this problem, we must prevent that mut references to self-referential structs can be created. Pinbox T and unpin. The pinning API provides a solution to the mut T problem in the form of the pin wrapper type and the unpin marker trait. The idea behind these types is to gate all methods of pin that can be used to get mut references to the wrapped value, e.g. getMut or derefMut, on the unpin trait. The unpin trait is an auto trait, which is automatically implemented for all types except types that explicitly opt out. By making self-referential structs opt out of unpin, there is no safe way to get a mut T from a pin box T type for them. As a result, their internal self-references are guaranteed to stay valid. As an example, let's update the self-referential type from above to opt out of unpin. Phantom pinned. We opt out by adding a second _pin field of type phantom pinned. This type is a zero-sized marker type whose only purpose is to not implement the unpin trait. Because of the way auto traits work, a single field that is not unpin suffices to make the complete struct opt out of unpin. The second step is to change the box self-referential type in the example to a pin box self-referential type. The easiest way to do this is to use the box pin function instead of the box new for creating the heap allocated value. In addition to changing box new to box pin, we also need to add the new _pin field in the struct initializer. Since phantom pinned is a zero-size type, we only need its type name to initialize it. When we try to run our adjust example now, we see it no longer works. Is this on the playground? Cannot assign. Cannot borrow data in a dereference of pin box self-referential as mutable. Okay. Both errors occur because the pin box self-referential type no longer implements the derefMut trait. This is exactly what we wanted because the derefMut trait would return a mut reference which we want to prevent. This only happens because we both opted out of unpin and changed box new to box pin. What happens if you only do one of those two things? The problem now is that the compiler does not only prevent moving the type in line 16, but also forbids to initialize self-pointer field in line 10. This happens because the compiler can't differentiate between a valid and invalid uses of mut references. To get the initialization working again, we have to use the unsafe get unchecked mute method. Safe because modifying a field doesn't move the whole struct. All right. Right, so now we actually get to mark it as unsafe, which is better, right? Because now we know that we the human have to guarantee that this is safe. Oh, it still doesn't compile. Oops. Now the only error left is the desired error on mem replace. Right, we don't want mem replace to be able to fail. But we do want to be able to set the value, so that's why we did this. Okay. Remember, this operation tries to move the heap allocated value to stack, which would break the self-reference stored in self-pointer field. By opting out of unpin and using pinbox-t, we can prevent this operation at compile time and thus safely work with self-referential structs. As we saw, the compiler is not able to prove that the creation of the self-reference is safe yet, so we need to use an unsafe block to verify the correctness ourselves. Stack pinning and the pin mute t. In the previous section, we learned how to create pinbox t to safely create a heap allocated self-referential value. While this approach works and is fine, while this approach works fine and is relatively safe apart from the unsafe construction, well, see, this is what bugs me about the word unsafe, the keyword unsafe, is that we're not doing something unsafe. We're doing something safe, but the compiler can't tell that it's safe. So we have to tell the compiler that it's safe. So maybe it should have been called safe instead. And the compiler should say, this looks unsafe to me. Is it safe? And then we wrap it in a safe block. While this approach works fine and is relatively safe, the required heap allocation comes with a performance cost. Since Rust always wants to provide zero-cost abstractions when possible, the pinning API also allows to create pin mute t instances that point to stack allocated values. Unlike pinbox t instances which have ownership of the wrapped value, pin mute t instances only temporarily borrow the wrapped value. This makes things more complicated as it requires a programmer to ensure additional guarantees themselves. Most importantly, a pin mute t must stay pinned for the whole lifetime of the referenced t, which can be difficult to verify for stack-based variables. To help with this, crates like pin utils exist, but I still wouldn't recommend pinning to the stack unless you really know what you're doing. For further reading, check out the documentation of the pin module and the pin new unchecked method. Pinning and futures. As we already saw in this post, the future poll method uses pinning in the form of pin mute self parameter. The reason that this method takes a self pin mute self instead of a normal mute self is that future instances created from async await are often self-referential, as we saw above. By wrapping self into pin and letting the compiler opt out of unpin for self-referential futures generated from async await, it's guaranteed that the futures are not moved in memory between poll calls. This ensures that all internal references are still valid. It's worth noting that moving futures before the first poll call is fine. This is a result of the fact that futures are lazy and do nothing until they're polled for the first time. The start state of the generated state machines therefore only contains this function arguments, but no internal references. In order to call poll, the caller must wrap the future into pin first, which ensures that the future cannot be moved in memory anymore. Since stack pinning is more difficult to get right, I recommend to always use box pin combined with pin as mute for this. In case you're interested in understanding how to safely implement the future combinator function using stack pinning yourself, take a look at the relatively short source of the map combinator method of the futures crate and the section about projections and structural pinning of the pin documentation. We could take a quick peek here, right? Yeah, this is what we were looking at before, right? Oh no, this is the map one. This is relatively straightforward, isn't it? Self is mute, calls future, calls poll with the context, map output. So that's interesting that our self can be a pin. That's something new. Normally you just see self, right? But this is saying that self is this different type. Because the self is map future F, but our this self is a pin of mute map future F. Okay. Executors and wakers. Using async await, it is possible to ergonomically work with futures in a completely asynchronous way. However, as we learned above, futures do nothing until they're polled. This means we have to call poll on them at some point, otherwise the asynchronous code is never executed. With a single future, we can always wait for each future manually using a loop as described above. However, this approach is very inefficient and not practical for programs that create a large number of futures. The most common solution for this problem is to define a global executor function that is responsible for polling all futures in the system until they are finished. Executors. I don't know. They got to be pronounced one way or the other. Maybe both are acceptable. The purpose of an executor is to allow spawning futures as independent tasks, typically through some sort of spawn method. The executor is then responsible for polling all futures until they are completed. The big advantage of managing all futures in a central place is that the executor can switch to different future whenever a future returns poll pending. Thus, asynchronous operations are run in parallel and the CPU is kept busy. Many executor implementations can also take advantage of systems with multiple CPU cores. They create a thread pool that is able to utilize all cores if there is enough work available and use techniques such as work stealing to balance the load between cores. There are also special executor implementations for embedded systems that optimize for low latency and memory overhead. To avoid the overhead of polling futures over and over again, executors typically also take advantage of the Waker API supported by Rust's futures. The idea behind the Waker API is that a special Waker type is passed to each invocation of poll wrapped in the context type. This Waker type is created by the executor and can be used by the asynchronous task to signal its partial completion. As a result, the executor does not need to call poll on a future that previously returned poll pending until it is notified by the corresponding Waker. This is best illustrated by a small example. So here's async function write file, which calls async write file .await. This function asynchronously writes the string hello to a foo.txt file. Since hard disk writes take some time, the first poll call in this future will likely return poll pending. However, the hard disk driver will internally store the Waker passed to the poll call and use it to notify the executor when the file was written to disk. This way, the executor does not need to waste any time trying to poll the future again before it receives the Waker notification. We will see how the Waker type works in detail when we create our own executor with Waker support in the implementation section of this post. Cooperative multitasking ? At the beginning of this post, we talked about preemptive and cooperative multitasking. While preemptive multitasking relies on the operating system to forcibly switch between running tasks, cooperative multitasking requires that the tasks voluntarily give up control of the CPU through a yield operation on a regular basis. The big advantage of cooperative approach is that tasks can save their state themselves, which results in more efficient context switches and makes it possible to share the same call stack between tasks. It might not be immediately apparent, but futures and async await are an implementation of the cooperative multitasking pattern. Each future that is added to the executor, is basically a cooperative task. Instead of using an explicit yield operation, futures give up control of the CPU core by returning poll pending or poll ready at the end. There's nothing that forces futures to give up the CPU if they want. They can never return from poll, e.g. by spinning endlessly in a loop. Cradell, thank you for the follow. Much appreciated. Since each future can block the execution of the other futures in the executor, we need to trust them to be not malicious. Futures internally store all the state they need to continue execution on the next poll call. With async await, the compiler automatically detects all variables that are needed and stores them inside the generated state machine. Only the minimum state required for continuation is saved. Since the poll method gives up the call stack when it returns, the same stack can be used for polling other futures. We see that futures and async await fit the cooperative multitasking pattern perfectly. They just used some different terminology. In the following, we will therefore use the term task and future interchangeably. Okay, then we go into implementation, but I've already spent an hour and a half on this, and my voice is going, and this would be good for the next stream, right? I'm just scanning through here. Then we're doing keyboard input, yeah. Okay, so what we're going to do then is we're going to wrap the stream up here in terms of async await.